Okay, the topic for today, okay, we will actually look at the electronegativity. Okay, when it comes to electronegativity, we need to understand, okay, what is the definition of electronegativity. Okay, electronegativity is defined, okay, as the ability, okay, ability of any atom, okay, of any atom to pull the electron, okay, or to pull the electron pair. And this electron pair is not actually any kind of electron pair, okay. We cannot just simply pull any electron. So for electronegativity, the electron pair that they actually meant is covalently bonded electron pair. Covalently bonded electron pair to itself. To itself. Now, if I actually put it in a sense of HCl, okay, if we have HCl, okay, we might actually think that the cross dot diagram, it looks like this. We might think that HCl, the electrons, the shared electron, okay, the bonding pair of electron, they might be perfectly in the middle. Okay, we think like that. Okay, but in reality, okay, it is not perfectly in the middle. So if I just put it over here, if we think that the electron are going to be somewhere in the middle over here, that is not true. Okay, that is not true. Okay, do remember HCl is a covalent molecule. Okay, they have different atoms over here, which is going to be hydrogen and chlorine. Okay, those two atoms, they have different ability to attract electron pair. Okay, they have different ability to attract electron pair. And this ability, we can actually identify by roughly looking at our periodic table. Okay, so when we look at our periodic table, okay, we can actually identify a little bit about electronegativity. Electronegativity, I just told you that they are ability to attract electrons. Okay, in order to attract electrons, okay, what do you need? Okay, let's actually see from you guys. Jordan, in order to attract electrons, what do you think that you need? Let's say this is A. Okay, in order to attract another electrons over here, so what do you need? Okay, there's going to be another, let's say this is electron and this is another one atom. You want to attract this electron. What you need actually?
This proton.
Yes, okay, you need a very strong proton because electron is negative. So of course you need to be having a very a lot of proton that will actually contribute to your nuclear charge. Okay, so nuclear charge is that's a term that we use. Okay, if you have more proton, it means your nuclear charge is more, but cannot be simply just nuclear charge because nuclear charge is very relative. Okay, why relative? Because okay, we have other factors that will contribute to this. For example, distance, okay, of the nucleus, because do remember, proton, they are always in the middle, okay, in the nucleus itself. Okay, so if the electrons are further away, okay, the distance or the atomic radius is too big, of course the nuclear charge is not going to be very strong. Okay, that's distance. And we have learned about shielding effect. Okay, can someone actually help me? What is shielding effect? Josh, can you tell me what is shielding effect?
It's like electrons repelling
Mm-hmm.
each other in the atomic like orbitals. So like
Mm-hmm.
it's easier to ionize the element itself.
Okay, basically the shielding effect is when you have a lot of electrons in between. So it will actually it will cancel out the attraction of the nucleus towards the other electrons. Okay, so because they are negatively charged. So if let's say this is going to be the nucleus, okay, if they are holding the electrons strongly, okay, let's say they are holding the electrons strongly. Okay, imagine these are hands and then the nucleus is trying to hold the electrons. If you have a lot of electrons in between, okay, they will actually behave like some kind of a shield, okay, they will behave like some kind of shield that will prevent, okay, that will prevent that will prevent, okay, the nucleus from trying to pull the electrons. So it means the strength from here, when you go and try to actually get the electrons over here, it will be kind of cancel out. So by the time they go over here, it's going to be already weakened. Okay, so it's a weak attraction. So do remember, like when you have a big atomic radius, okay, it is going to be, if you have a lot of shells, okay, it means the electrons are going to cancel out the nuclear charge. Okay, it's going to actually make the attraction to become weaker. Okay, now when we look at your periodic table, this is periodic table. Let's say we go across a particular period. Okay, if you go across a particular period, we know the atomic radius supposed to go down or supposed to decrease. What is the reason? I already mentioned to you last time when we learned, okay, when you go across the periodic table, we know the proton number increases. Okay, when the proton number increases, okay, we know that in the same period, okay, the number of shell remains the same. Okay, there is only the same number of shells. So if the shell and, okay, the shielding effect, if they actually remain constant, okay, the number of shells and shielding effect remains constant, that actually makes that, okay, your proton number is the only one responsible for your nuclear charge. And we can say that your nuclear charge is increasing as you go across the periodic table. Okay, and what does it do? It means that, okay, your proton have a greater attraction towards those electrons and they tend to pull them all closer. Okay, it means that they are really, really strong. So they also have, when it comes to electronegativity, you can just simply say, as you go across the periodic table, you can just say the electronegativity increases as well, because, okay, they can actually attract, okay, the ability to attract the covalently bonded electrons would be more because they are smaller. Okay, the nuclear charge is higher. Okay, they can actually attract the covalently bonded electrons. But the situation is going to be different if you go down the same group. Why? Because you might have, okay, the number of shells are going to increase, and then the size is getting bigger and bigger. If the size are getting bigger and bigger, it means, okay, again, even though your proton is increasing, but we can say the distance, okay, from the nucleus, okay, and then to the distance is actually getting bigger. Okay, so wait, yeah, let me check. Okay, can you see me? My connection is not so stable, but you can see here. Okay, I just wrote about proton. Okay, proton increases, the distance also increases. At the same time, okay, I can also say that, okay, my shielding effect, because a lot of number of shells are increasing, therefore I can say that my shielding effect is also going to become increased as well. Now these two factors, okay, these two factors will some sort outweigh, okay, they will outweigh the increase in proton number. So if I actually erase this part, okay, I can actually say that, okay, as I go down, okay, the group, okay, as I go down the group, my electronegativity, okay, electronegativity will decrease. Okay, my electronegativity decreases. Why? Okay, because my distance, increase in distance and shielding effect will outweigh the increase in proton number. So that actually makes the attraction, okay, that makes the attraction of this nucleus, okay, or the proton, okay, to attract the electrons will be weaker. Okay, so to summarize, okay, how do we summarize this? Okay, if we have a periodic table, okay, when I go across the periodic table, I can say that my electronegativity, okay, I just put En, my electronegativity actually increases. When I go down, okay, because of my distance and the shielding effect outweighs the increase of number of proton, I can say that, okay, my electronegativity is going to go down, decreases, okay, decreases. Now, using this concept, okay, we can also know that, just take note, if you are actually arranging in a form of scale, okay, there must be something that is very less electronegative, and there must be some element that is going to be very highly electronegative. Okay, similar like when you are having a class, there must be a student that is very having the lowest mark, and there must be a student that is having the highest mark. Now, in this case, okay, for electronegativity, do remember the person who's having the lowest mark over here, or the lowest electronegativity, is hydrogen. And that is going to be really helpful for you, because hydrogen is weaker compared to other elements. Okay, hydrogen is weaker compared to other elements. You can actually memorize this. Okay, it will be helpful to actually identify why I think hydrogen only one proton. Okay, one proton, the nuclear charge is not so enough. And then they want to actually attract the electrons. It's going to be very difficult. Okay, so this one is outside of your syllabus, which is, I think, when it comes to electronegativity, there should be some kind of a scale. Okay, like for example, let's say in a chemistry mark, we have a scale. Okay, 0 to 100%. Okay, let's say 50% is your passing mark or something. There is some sort of a scale. Okay, 80% is A, for example. There is a scale. In electronegativity, there is also a scale, okay, but it's not in your syllabus. They call it Pauling scale. Okay, according to Pauling scale, okay, they have given the number 0 to 4. 0 is being the least electronegative, 4 being the highest electronegative. Okay, you can actually take note of this. But whatever it is, let's actually come back to this example now. Okay, according to this example, okay, if you have HCl, I just told you that H is going to be the least electronegative. It means it's the weakest. Okay, it's the weakest. Therefore, okay, we know that Cl, okay, Cl being somewhere here in your periodic table, of course, is going to be higher electronegativity. Okay, so what happens is the electrons, okay, these two electrons, they are going to be pulled closer towards Cl. It means now the electrons are no longer going to be in the middle. They are going to be closer towards Cl. Now, if I put it in form of molecule, okay, imagine I just put in form of molecule. Okay, what happens here is I will have most of my electron to be towards my right hand side. When they are more electron towards right hand side, the total the charge is going to be not so symmetrically distributed. They are going to be like, there will be one part of this molecule have more electron, one part of this molecule will have less electron. In this case, okay, the Cl will have more electron, therefore they will have a delta negative, a partially negative charge. Why? Because they contain more electrons towards the Cl. And since they don't have a lot of electron, there is going to be a partial positive for the H. Okay, this creation of partial positive and partial negative will actually tell us that, okay, that this particular molecule, okay, this particular molecule has dipole. Now, what is the meaning of dipole? Dipole means, okay, di means two, pole means polarity. It means there's going to be positive and negative. So if you have this delta positive and delta negative, we call this molecule being having dipole. Okay, dipole, positive and negative. Okay, now if you have, for example, okay, if I have, for example, Cl and Cl, and then you are sharing the electrons. Now, do you think, okay, do you think that this Cl2, okay, if I just put Cl and Cl, do you think the electrons are still going to be in the middle, or do you think that they will go somewhere to the left or to the right? What do you think, Jordan? What do you think, Jordan? Do you think it will stay in the middle, or do you think it will go somewhere else?
I think I'll stay in the middle.
Yes. Why did you actually mention, why you feel that they will stay in the middle?
Their charge, both of them is the same.
Or to be actually exact, can we actually relate to the concept that we learned earlier about electronegativity? What can you say about the electronegativity of both of these atoms?
Both of their delta is equal, no like delta positive or negative.
Yeah, rather than saying that, you can say that, okay, both of them are same atom. Therefore, okay, they have the same electronegativity. So what is the definition of electronegativity? Ability to pull the covalently bonded electrons to itself. So if they are pulling with the same strength left and right, okay, it means that they are still going to stay in the middle. So the electrons will stay in the middle. Therefore, okay, it will not affect the electrons. So they will actually stay like usual. There is no delta positive, there's no delta negative. Okay, it's going to be the electrons are equally distributed. So we don't have any problem. Okay, so we call this, okay, not having dipole. Okay, sometimes to write them as having dipole and not having dipole is too long. Okay, so what they actually came up with a term to show that, okay, if they have dipole, what we should call them. If they have dipole, we call them as polar molecule. Okay, if they have dipole, we call them as polar molecule. If they don't have dipole, we call them non-polar molecule. Okay, polar molecules and non-polar molecules. So let's actually go and look at some of the examples, okay, of these molecules, okay, related to polar and non-polar. Okay, so we actually learn about polar and non-polar molecules now. Now, in order to actually identify the molecules, whether they have polar and non-polar, we have to look first, we have to look at the atoms that is bonded. Okay, we have to look at the atom that is bonded. Second, we have to look at the lone pair of electrons. Okay, we also have to look at the symmetry of the molecule. Okay, what is meant by symmetry of the molecule? Okay, because, okay, when we actually learn about bonding, okay, we have learned a lot of types of shapes of molecule. Okay, one of the example is linear. Okay, for example, BeCl2. It's a linear. So if it is linear, of course, it's symmetry. Okay, if it is symmetry. Another type of symmetry molecule is going to be CH4. They are tetrahedral. Okay, so they are symmetry as well. BF3 is symmetrical as well. Trigonal planar, 120 degrees. They're symmetrical. Now, we do have molecules that are non-symmetrical. Example, this is going to be non-symmetrical molecule. This is going to be non-symmetrical molecules. Okay, symmetry means you can separate them. Okay, you can separate. Yeah, you can separate. Okay, you can divide it into 4. Okay, you can divide it into 3. Okay, unsymmetry, or they are not symmetric, it means that you cannot just simply divide them. Okay, so that is going to be the 3 criteria that we will look to identify a molecule, whether they are polar or non-polar. Okay, so let's actually look at some examples. Okay, one example that I want to actually highlight, I think earlier, let's say we look at BeCl2. Now, BeCl2 is a very interesting molecule, okay, because okay, when we look at the atom, okay, when we look at the atom, we actually look, okay, there is going to be Be, there's Cl, there's Cl, and they belong to group 2, therefore they have something like this, okay. Of course, I didn't balance for the chlorine, but these are important things that I need for BeCl2, and I don't have any lone pair, so forget about lone pair. According to atom, I have two different atoms over here, chlorine and Be. And I know when I look at your at the periodic table, I know Cl is somewhere here, Be is somewhere here. Which one do you think is more electronegative, Jordan? Be or Cl?
Cl.
Okay, Cl being more electronegative. It means they will pull the electrons towards Cl. They will pull the electron towards the Cl. Okay. Now, if I ask you whether the bond, the BeCl bond, are they polar? Okay. Of course, they are polar. Why? They are not going to stay in the middle. Okay. It's pulling towards Cl. Okay. Of course, the bond is polar. Okay, the bond is polar. But in order to determine polar and non-polar, okay, that is not the only thing that we look. Okay, we still need to look at the symmetry of the molecule. Now, imagine like in physics, okay, when there is two people pulling with the same force to left and right. It's a symmetrical molecule. Okay, the electrons, okay, will be pulled at equal force, and they will be equally distributed. Okay, therefore, even though the BeCl bond is polar, okay, and there is a dipole, we call it something like your physics here, we call it dipole moment. Okay, there is a dipole there. Okay, so there is delta negative and delta positive here, delta negative, delta positive here. The delta negative and delta positive, we call it a dipole moment. Okay, dipole moment. So what happens over here, the dipole moment in a symmetrical molecule will cancel each other. Okay, they will cancel each other, and this thing will only happen if they are in a symmetry molecule. Okay, they will cancel each other. And what is the consequences of that? This polar bonded molecule, they will become non-polar. There is no partial positive, partial negative, because it's going to be cancelled out. Okay, so if I actually look at it in a different example, yeah. Okay, if I have another example, BF3. Okay, again the same thing. Okay, if I have your periodic table, B is somewhere here, F is somewhere here. Okay, group 17. F is more electronegative than B. They will pull the electron towards F. But do remember something like your physics, they are pulling the electrons at 120 degrees to each other, and then they are going to be pulled in the same force. So what happens, you will actually, in physics, they call it equilibrium. Okay, they will reach equilibrium where they are not moving. So basically what we have over here is the electrons will actually arrange itself so that they are going to be equally distributed within the molecule. If they are equally distributed, in this case, even though the bond is polar, okay, the bond is polar, the entire molecule, okay, the entire molecule is non-polar. Why the entire molecule is non-polar? Because the dipole moment cancels each other out. Okay, cancel each other out. Okay, now I'll give you another example. Okay, another example is, okay, if you have ammonia. Now, this is going to be different because this is not going to be a symmetrical molecule. And if I have periodic table, hydrogen is the lowest, yeah, I told you, the weakest electronegativity. Nitrogen is somewhere here, group 15, group 5. Okay, so they can actually pull the electron. So what happens? Nitrogen pull the electron. Nitrogen pull the electron. Nitrogen pull the electron. Now, first you look at the atom. Okay. Second, we look at the symmetry of the molecule. It's not symmetrical. And then there is actually another one is lone pair of electron. Lone pair of electron, they themselves, okay, what actually happens here? If I put this molecule in form of a triangle, I can feel that the top part of the triangle will be more delta negative, okay, because all the electrons will go there. All the electrons here will be less, okay, delta positive. It means I can say there is a dipole over here. So I call ammonia molecule as polar molecule. Okay, the same applies, okay, when you have water, oxygen, H. Okay, if you have here hydrogen and oxygen, oxygen will pull the electron. Okay, there is going to be two lone pair of electron. So if I put it in form of a box over here, I know that this part, the top part of the box over here, will have a lot of electron, delta negative. Here will be less electron, delta positive, and I can say that this molecule is polar, okay, because there's a plus, partially positive and partially negative. So what happens if you have a symmetrical molecule, but you have different atoms? That is going to be also different, yeah? So if you have different atoms like this, okay, what happens? Okay, this is a symmetrical molecule, but I know compared to carbon and chlorine, carbon is here, chlorine is here. Of course, chlorine is more electronegative. They will pull the electron towards itself. So what happens here is if I actually have this molecule, this part of the molecule will be partially negative. This part is going to be partially positive, okay, because the electron goes towards the Cl. So I can say that this molecule is polar, okay. But if I have similar situation and I have Cl, and Cl, that's going to be different. Because, okay, the Cl will pull the electron, will pull the electron, will pull the electron, pull electron. So it is going to be equally distributed. So we don't have any polarity over here. So we call this molecule as non-polar. Okay, this is going to be generally something that we need to analyze one by one. Okay, but you need to understand the concept if you want to actually identify whether something is polar and non-polar. Okay, you need to actually have, okay, you have to look at the atom, you need to look at the lone pair, and you need to look at the symmetry of the molecule. So that is very important. So therefore we can actually identify based on this electronegativity, we can identify polar and non-polar. Okay, so now let us actually check what do you understand from today's lesson. Okay,